Okay, perfect. So it's my pleasure to present our research on the sheet music composer identification using deep neural network. So today in this workshop, on the behalf of my team, I will be present our work. So my name is Dnyanesh. Currently, I'm working as a computer vision scientist at Veridium in Oxford. So this research project was a part of my master's thesis. And our co-authors are Elona, so she is a part of this conference as well. György, he's a senior professor in Queen Mary University of London, and Ben, he's a R&D head at Stensberg. So we present a comparative analysis and end-to-end deep neural network model for identification of the music composers using visual representations of the sheet music. So you can see in this slide, okay. So based on our knowledge, this is the first time that the music composer identification has been addressed directly using visual representations of the music scores with a deep neural network without being dependent on conversion to any other intermediate music digital semantic format. Okay, so motivation of our project is to address composer identification based on visual representations. So in the last few years, music has been preserved in the form of the pictures, or we could say in the form of sheet music. Yeah, we are all aware about that. So the description of the composition style, if we can recognize or identify from the sheet music, it would serve as a complementary tool in musicological analysis of the historical compositions, or we can say with the handwritten compositions presented in the visual formats. Sorry. So for generating music recommendations or in digital instrumental applications, so it is useful and it has many array of purposes and it is useful in many digital applications. So composers have very distinctive personalities, right? So you might all aware about that. So they use a specific kind of sensitive and expressive way to represent their music into the music sheets. So composer can be identified by looking at their music score or by looking at their sheet music, right? So but human capability of identifying composers just by seeing visual representations are limited. So in the previous related work, so in this slide you can see, so in the past research, three approaches dominant composer identification work. So first approach is based on the digital semantic representations of the sheet music, which includes MIDI, music XML-like files as input data. Second approach utilizes the optical music recognition, right, OMR, so in which musical notes are recognized as object condensed to the bootleg scores, and from their music is extracted as a symbols or in the sequence of words, and after that using language-based model we can identify the composers. So and third approach involves the identifying of the composers using visual representations of the sheet music. So that's the part of our research and intensive experiments. Okay. So in this particular table, you can see most of the research focuses on the first two approaches, which use intermediate digital semantic representations extracted from the music sheets or MIDI to the identify composers. And for these references, you will get from our research paper. So just for displaying, I just got this table for you guys. So you can see here most of the research is focused on the intermediate representations of the sheet music. But since we are focusing on the visual representations of the sheet music without any intermediate conversion, and in the second approach, we are focusing on the bootleg score. But again, that we are going to utilize just the visual representations of the bootleg scores as well. So it is very unique among all past research in this field. Okay. So while addressing this problem, the representations of the music data is very important for composer identification, and the methodology of the identification differs based on it. So if you are selecting MIDI files, audio files, or music XMLs, our methodology will be very different. And if we are going to deal with them with just visual representation, then the identifications of the composer methodology will be different, right? So in our particular research, we choose the two data sets in the two way of representations. The first is the sheet music images, and the second is the corresponding scores into the bootleg scores. So same sheet music images we have converted to the bootleg score representations. So see how our model is work on those visual representations of the bootleg score, right? So if our model works better with the music sheet images directly without doing any intermediate conversion, then it might be work better with the bootleg score representations as well. So, but again, we know there is so many constraints on data sets. So we try to gather sheet music images from the IMSLP. And because of the limitations of the publicly available data, we used so many MIDF files of the composers to generate the sheet music images using Dorico Pro software, which is basically provided by our industry partners, Work Media Technologies. And we try to maintain combination of low resolution images from the very old historical composition style data and with the very old, very high resolution music score images, which we generated using the Dorico software with the use of MIDF files. So it makes our dataset versatile, and the combination of both makes the dataset more diverse in terms of features for our deep learning model. So while addressing this issue, we identified that the data distribution methods which we will use on our dataset plays very important role in training and getting inferences with a deep neural network. So second and the most important step in the identification of composer is, we can say, the distribution of the data in training and testing to avoid any biases. So based on the distribution of data, one can determine how accurate your trained neural model is, or we can identify of the sheet music images which were not used during training. So we considered some portion of scores from all composers, you can see here, for training, and some portion for testing. So we were considering equal proportion in training, and it is possible to, sorry, so it is possible to minimize bias in training with the proposed data distribution method. And it has been found that the sheet music images without exposure to the model during training with this particular data distribution method are likely to be correctly identified with the exact style of the composer. So it has been demonstrated that our model is capable of learning certain specific patterns from this particular data distributions method. And this particular data distribution method is we proposed, but we haven't utilized in our experiments. So in the future work, we can utilize this particular, so in which we were planning to just expose some scores of composers to the training, and whole score from particular composer we will keep aside, and just we will train on these particular musical scores, and we will try to identify this musical style composer, so in which category it belongs, like that. So currently we are using this data distribution method, in which we are trying to distribute all the musical scores in equal proportion. So as a part of our initial experiments, we use some models architecture that are commonly employed in the field of computer vision in deep learning. So such as AlexNet, VG, ResNet. But however, the results were not satisfactory. So we switched to some other experiments and came up with a new model. And we name it as a CompIdNet. So its full form is Composer Identification Network. And this was inspired from the GoogleNet architecture. So and the CompIdNet architecture, on the other hand, it's complex, heavily engineered, and it uses a lot of tricks to push performance in the both terms of speed and accuracy based on the architecture of GoogleNet. So we will discuss these three architectures in the further slides. Oh, sorry. So our proposal is to make use of different versions of the inception blocks in the CompID network in order to reduce the computational complexity, overfitting, and to cover dense and sparse feature representations on a different music score sheets in order to increase the performance on both the speed and accuracy front. So considering the depth of the network, we assume that the composer identification network is likely to suffer from the vanishing gradient problem, but again, which we are able to prevent by adding an auxiliary classifier. So you can see here, we are adding two auxiliary classifiers in between of the model. And auxiliary classifier, the softmax function is applied at the end of the network with the inception blocks. And in order to calculate the total loss, real loss is added up with the weighting sum of the auxiliary losses, and then both the numbers are summed up with the total loss, basically. Okay, so based on the inception version v1 architecture, composer identification version 1 is designed, which contains the 7 inception layers stacked on the each other linearly. We added auxiliary classifier as we discussed, And the convolutional happens in the three sizes of the filters, right? So we are utilizing 1x1, 3x3, and the 5x5 kernels on the same level along with the max pooling. And 1x1 convolution is added before the 3x3 and the 5x5 convolution to reduce the number of parameters and to reduce the ultimately the size of the model, because we know the GoogleNet architecture is very complex, and we are developing the composite identification network based on that architecture. So size of network was going to be very high. So we tried to reduce some inception blocks, and we tried to use some factorization techniques to make our network more computationally worthy and with achieving the good accuracy. So this was our first version. After doing some experiments on this network, we tried to modify that and we come up with the composite identification network version 2. So in composite identification network version 2 improved the composite identification network version 1 basically by reducing the computational complexity even further. It was possible to improve the efficiency of the convolution by using smart factorization method, which we utilize in version 1 as well. So the network's computational cost is reduced when convolutions with the n cross n filter size we utilize with the 1 cross n and n cross 1. So that is known as basically the factorization techniques which we use in the deep learning. But by the dimension reduction methods to an extreme, you might be losing information while training. So this is known as, again, representation bottleneck in the GoogleNet architecture. So in the composite identification network version 2, filters are expanded in parallel. So you can see in this short diagram. So we try to expand our architecture parallelly and in depth as well. So it removed the representation bottleneck, and the specialized reduction blocks were added feature in this model. So you can see some reduction blocks we have added, which were not included in the version 1. So which is used to change the height and width of the grid. So again, it is useful in the making model model complexity less and with the good accuracy. So again, we improved the version 2 based on the performance of that, because we reduced the complexity in the version 2, but the accuracy got reduced. So we were targeting good accuracy. So again, we changed that modification and we utilized the Inception's version 4 blocks from the GoogleNet architecture in this network. And compared to the Inception v2 counterpart, the three main Inception modules, you can see A, B, and C blocks were introduced in this particular architecture. So I will not go so deep in this particular architecture. So training methodology. So now let's discuss about the experiments. So we categorize experiments into two categories. So in the first type of experiment, we used sheet music image dataset with the different deep neural network model. So in the proposed approach, there are three stages you can see in this diagram: pre-processing, training, and the classification. So in order to maintain uniformity throughout the dataset, all sheet music images we converted to the grayscale during pre-processing stage. And in order to minimize the effect of lightning conditions, background subtractions was applied. And for that, we used Gaussian blur filter and the foreground mask. And after that, we come up with the resultant image. And those particular images, pre-processed image, we use for training. So with these particular experiments, these are some results. So you can see, as I mentioned in earlier slides, so AlexNet, ResNet, and VGG were not giving satisfactory results, but our version 1, version 2, and the version 3 are giving good results. And on the in compared to all these three versions, version 1 and version 3 was giving the good results. So we evaluate the performance of all these 6 different architectures. And in addition, there will be trade-off between accuracy and computation time. So as we know, so in computation, in the version 1 architecture of our network, we were not utilizing any factorization techniques or any reduction blocks or any parallelization technique. So version 1 was taking much more time than V2 and V3. V2 was taking less time because we modified it so much. We used multiple factorization techniques, but version 2 was not giving good results. And again, with the V3, computational time in compared to version 2 was higher, but accuracy was good enough in compared to version 2. So we can say in comparison with all these three models, CompIdNet version 3 model, which was inspired from the inception block version 4 from the GoogleNet architecture, shows the best results. And it also has the largest computation time. For the same computation time, VGG and resonance were totally failure, basically. Okay. So yeah, in this diagram, you can see this is the F1 score plot. So CompIdNet version 1 and the version 3 are with the blue and the gray color. So these both are giving good results consistently, but all others are not that much. And the version 2 was good enough in the comparison to the VGG, AlexNet, and the ResNet, but it was not good enough in the comparison to the V1 and V3. Okay. So in second experiments, the experiment, okay, this was the classification. In second experiments, we use the same data distribution as before, but however, the number of images decreased during the conversion of the music sheet images to the bootleg score due to the poor quality, right? So we tried to convert all those musical sheet images to the bootleg score, but somewhere from the historical representation, somewhere with the very poor quality. So those images, we were not able to convert those into the bootleg representation. And those bootleg score images, again, we use with our same model, and we try to identify the composers of the music sheet based on this bootleg score representation. So if you see in this particular diagram, again, so version 1 and the version 3 of our composer identification network was giving the good results. But the version 2 was giving less results compared to the V3 and V1, and the AlexNet, ResNet, and VGG could not give the best result at all. AlexNet was better. It was giving around 65 to 70 sometime, but ResNet and VGG was not giving the good results with the same data distribution. Okay, so I will try to summarize.
Please come to a conclusion.
Yeah. Sorry. So our study proposes a method to reduce the dependency of composer identification on intermediate representation in the identification of composer, basically. So we are reducing that dependency. The effect of this is that we are able to reduce the likelihood of information loss during the conversion process as a result. And we collected music sheet images from the variety of composers, composer scores as a part of the process for creating our data set. The next step in our process was to extract the bootleg representation from same musical scores and same material, basically, so and same data distribution. So during the same experiment period, two different set of instruments conducted, and the first set of experiments examined the performance of the deep neural network model based on the music sheet, and the second examines the performance on the bootleg score. And we can conclude that we found that the visual representations of the sheet music were giving the effective for the identifying composers than visual representations of the bootleg score. And the result of our study again indicate that neural network architecture that include a combination of smaller and the larger kernels, as we are using multiple kernels in the version 4 and the version 1 of the inception blocks. So which works better on the sheet music representation. And we proposed a new type of data distributions method, which again contributed a lot in our research. But we, in future work, we can utilize different data distributions, different set of data, and we can try to experiment that how it will work on those data distributions. So thank you. I was aware that I was having less time, so I was trying to just rush up with everything. Sorry about that.
Okay. Thank you very much. Okay. Thank you very much.